now, so thank you. All good, Alison?
All ready to go, Nick. Thank you.
Yeah. All right, thank you all for coming tonight. Glad you could make it. And I hope you have had a drink sponsored by Geoimage, which is Mark's company. Thank you, Mark. Before we get fully underway, I'm just going to go through a few housekeeping. This is one of the webinar series, as you can see there. And I would love to have this to work. She's not working this time. Hold on. There we go. The ASEG would like to acknowledge the traditional, the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognise their continuing connection to these lands, water and culture, and pay our respects to the elders past and present. We'd also like to thank our Corporates Plus and corporate members for their support, and thank you to our branch sponsors as well. All right. If you have a question, please click on the Q&A function and then leave your message. I believe Alison might be helping us with that, or maybe James, and we'll probably answer the questions at the end of the talk. Thank you. We have some upcoming webinars, as you can see there, with more information online. I'll go through a few other bits and pieces for the Queensland branch in a second. And just in case you're wondering what the member benefits are, and this is probably good for those who are attending for the first time tonight, we have a long list of benefits, including free access to exploration geophysics, a free copy of Preview, which is our bi-monthly magazine, which is pretty awesome, reduced entry to the AGC conferences, which are very, very popular. The next one is in Brisbane in 2023. Free entry to the technical events. We usually put on a bit of food, and if there's a sponsor, we add some drink. Access to the wine offer, social events. You can read the rest. Yes, that's right. It's amazing, Patrick. Right, and to keep in touch, we have monthly email newsletters going out to emails, and there are socials. Yes, we're also getting more and more involved in LinkedIn. So, rightio. Now, just want to make a few branch announcements. The AGM will be held next month on the 17th of May. Maybe some changes to the committee. We're trying to expand the size. We compared ourselves to the other branches, and we're going off only a fair few, only a few. So we'll probably hopefully get some more volunteers. If anyone wants to volunteer, please email me, or email me at the Queensland Secretary at aseg.org.au. We'll say by the 7th of May, please. The AGM will be held alongside Dr. Adrian McCullum's talk. He'll be presenting about his visit to Antarctica, and probably along with a few of his engineering exploits. So please come to that. It's not going to be purely technical, but it'll be quite interesting. Thank you, Hank, for setting that up. Finally, we're looking for more speakers for the end of the year, July and beyond. Feel free to email suggestions or come up to me and let me know. So, on to tonight's talk. Mark, you can get your presentation. Mark Covington is an enterprise solutions manager from Geoimage, and his talk tonight will be on current space and satellite technology. Mark graduated from the University of Queensland with honours in geophysics in the mid-1980s. and cut his teeth in exploration geophysics in northwest Queensland, exploring for copper and gold for placer exploration. Years sleeping in swags under the open skies, relying on GPS receiver the size of a shoebox to navigate the inhospitable coordinates indirectly exposed Mark to his first dependency on satellites. 30 years later, Mark is again relying on satellites, this time to help industry solve a range of challenging issues, from remote exploring in South America using SWIR to using radar for measuring sub-millimeter subsidence in mine tailings dams, for monitoring vegetation rehabilitation in the PNG to measuring methane leaks on gas well pads. Mark enjoys judo, solving puzzles, and a glass of red, and it needs to be in that order. So please welcome Mark.
Thanks very much for that introduction. Sounds like something I would write about myself. Sorry about the delay in the proceedings this evening, everybody. A few technical issues, but there seems to be par for the course these days. I don't know how many Teams meetings and Zoom meetings I join every single day, and there's always some kind of issue for some reason. But we're here now, so that's the main thing. I do have a little bag of goodies there, so we'll be asking a few questions during the course of proceedings. So, you know, listen carefully, and you might score something that you like, or you might score something that you don't like it. Let's see how we go. So I just wanted to start off, I guess, talking about Geoimage just a little bit. We've been around for 30 years, but I sort of delve into exactly what we do. And then I wanted to talk a little bit about the history of Earth observation as we know it, using satellites since the 1970s. We'll move on to optical and multispectral data collection, and then Swirl. I think when I was first asked to give this talk, I thought, well, what would be really relevant to exploration geophysicists, and going back to my early days in the field, probably Swirl and hyperspectral, you know, hold the most promise in terms of exploration, in terms of greenfields exploration. So I'm not actually an expert on Swirl, but I've got a few slides on Swirl there to whet the appetite, so to speak. And then I want to talk briefly about TriStereo DEM. And if you can tell me what TriStereo means, then you might actually win something from the bag of goodies. And then radar and InSAR, which is kind of my pet topic. So I'll be talking about that a little bit. And then just to finish off, just my thoughts about what the future holds in the world of satellite. And it really is changing very rapidly in the last probably 2 to 3 years. There's just real game changers occurring out there in terms of the resolution, the ground resolution that can be achieved, and the revisit rates. And I think in the next 5 years, it's going to make a big difference to not only mining and exploration industry, but a whole host of industries as well. So Geoimage, we were started in Queensland in 1988. The two founders actually worked for Mount Isa Mines back in the day, and they decided to start running a little business in a garage. So I guess their original startup company, you know, 30 odd years ago. And then it grew from there, and we did have offices across Australia at some stage, but now we're mostly focused just down the road in the valley, and we're very comfortable there. We have people work in WA and a few other places. We work across multiple industries, mostly mining and exploration. That's where we get most of our revenue from, probably about 65% of our revenue. Comes from infrastructure, government, and environmental monitoring. It says here we're Australia's only gold partner of Maxar. If you don't know Maxar, that probably won't mean too much to you, but by the end of this webinar, you'll know everything about Maxar, I'm sure. Why do clients choose us? Well, I guess we do have a longevity in the industry, have been around. It's quite a niche industry. Much like geophysicists, ourselves, you know, it's a fairly niche area. So we are a fairly trusted authority. You know, we have built relationships with world-leading owners of satellite systems, and so we are agnostic or independent, if you like, in terms of we don't try and promote one particular satellite over another one. We will talk to our clients, understand what they're trying to achieve in terms of the use case, and then we'll look at the portfolio of satellite sensors that we have available to us, and then talk about the best possible choice in terms of meeting that use case. In terms of course, economics, of course, always comes into the picture. So what's the best solution? Some of the clients that we that we have on our books, there's more than that, but it's just a brief smattering called BHP, Rio Tinto, Fortescue, UNE. So we do work with some of the universities as well. So they engage us on research more in the agricultural sense. So I just wanted to talk about the 50 years, and I actually did have a couple of videos that I found really intriguing last night, but I can't play them right now because I realized they're on a different screen. But I did have one from 1972. So this was the first, this was launch of Landsat back in 1972, and I had the video of the guys in mission control and the launch and everything, and it looked like to me an episode from Thunderbirds. For those of you that are familiar with Thunderbirds, it was so archaic, but back then it would have been so pioneering, absolutely incredible that they would have been launching this. And and Landsat is kind of synonymous with I guess Earth observation. It was really that first satellite that kind of set the standard, and it was focused. It was designed and built and launched, and its whole mission was about looking at the Earth, and that really kind of triggered a whole industry in terms of monitoring the Earth and the changes on the planet. And we fast forward to 2021, you can see satellites here. So this is the latest one. This is the Pleiades Neo satellite from Airbus, state of the art. It was launched mid last year. From French Guiana. I guess like in general terms, it doesn't look too different. You've got the solar panels here back in the 1970s, and you've got the same solar panels here, which are absolutely crucial for providing power. Maybe a little point of interest is that when they first go up into space, into their orbit, they actually turn and face the moon, and they go through a set of exercises where they actually calibrate the systems on board by looking at the moon, because the moon is very homogeneous and has certain reflectance characteristics that are then used to calibrate all the sensors before it then turns back and faces the Earth for the rest of its mission. And I did ask one of my colleagues at Airbus recently, I said, can we just direct it towards the moon and take a few shots? And that'd be really great in terms of marketing. And so he asked the question, he said, the problem is that when you turn the solar panels away from the sun, you're relying on the battery power, and that would be a big drain. And they really need those fuel resources in terms of changing the orbit of the satellite from every now and then. So they're always monitoring the position, down to a very small accuracy in terms of where those satellites are at any given time, because the accuracy of the satellite position is crucial in terms of the imagery that gets captured and the geospatial accuracy of that imagery. So, marketing opportunity gone begging, but anyway, it was worth asking the question at the time. My first prize at this point is really, I've got a choice between a hat, a Geoimage hat. Now I bought some umbrellas too, because when I left the office, it was looking like it could actually rain, a Geoimage umbrella. So anyone in the room who was actually alive in 1972, it's a bit of a cheeky question. Yes. Good on you, sir. Which one?
First university. I went to university because of Landsat is big news.
Yeah. So you're looking in the big news. Yeah.
I like that.
Yeah. Yeah. So that's right. I mean, those early courses at university, they're all really focused on Landsat and what you could do with the imagery from Landsat. That's exactly right. Oops. That's it. That's that. Yeah. lost control. Mouse is back.
Hi there, Mark. It's Alison here. Is it your mouse is not in control of your screen?
Oh, it's all right, Alison.
Yeah.
I've got the control back now. It's
Okay,
fine.
thank you.
That was just a YouTube video that was linked to the actual slide. So but it's all back. It's back now. Well, it was. Now it's gone again. Hang on a sec. Yeah. Now I don't know what's happened to my mouse. It's gone. I'll just have to go like this. Right. Okay. So that was a little soundbite of 1972. So quite antiquated these days, but again, as we said, pioneering at the time. So in terms of where we are, 50 years later, the range of satellites has increased tremendously. But probably up until the last 2 or 3 years, it was still very dominated by two big players, basically, sort of corporate, well, not corporate, country-sponsored players. So we're talking about countries like North America, Europe in terms of Airbus, Japan, ResTech, their sort of national space agency. It was a very expensive place to play in terms of designing, building. We're talking billions of dollars worth of investment to build a satellite, and many years, and even the most recent one. So even the most recent one, the Pleiades one. It's not actually not quite. Oh, here it is. Pleiades Neo is the most recent one that was launched last year. 2 of those satellites were launched here. It's actually what we call a quad constellation. So there's going to be 4 satellites in that constellation, another 2 to be launched at the end of this year. What that means is that you'll be collecting multiple times per day, every single day, at 30 centimeter resolution. So, about that kind of, you'll be able to determine something of that size, basically. A solid pixel would be about that size from space. Pleiades, so went up at 2014. It's got 50 centimeter resolution, swath width 20 kilometers, and then various other ones. These are all in the Airbus family, if you like, but Maxar has a similar family of different satellites for different things. We'll be looking at this little beast a bit later on, the TriStereo and Tenetrx and PAS. That's the radar satellite. So obviously a very specialized satellite. Spot 6-7, still, it's been around for a little while, but it's a pretty good at 1.5 meter resolution, 4 bands, and it's really good thing about 60 kilometer swath width. So it's a really wide swath width, which means you can cover really large areas in a short amount of time. And this graphic is really showing, I guess, in terms of the swath width, in terms of each one of those satellites, how the swath width compares. I guess the title really is spatial resolution versus swath width, because in general, the higher resolution you have, the smaller the swath width, and that is something to keep in mind when you're selecting, which sensor is appropriate for your use case. We have lots of clients that just come to us and say, we just want the highest resolution. We want 30 centimeters. And we'll say, well, what are you using it for? Well, we want to map a forest. So why do you really need to know at 30 centimeters where the limit of the forest is? I mean, 1.5 meters is surely going to be sufficient, for that use case. So it is about understanding what the use case is. In terms of exploration, I thought, what would be of interest for you guys. So satellite imagery, but also Swirl, shortwave infrared, and DEMs as well. So in terms of our exploration clients, these are probably the 3 things that we get asked about the most. So in terms of the optical, I won't go through all the details here, but as I said before, it's 50 centimeter. This is Legion, so this is Maxar, which is the I guess the rival to Airbus, if you like, in terms of the big boys or satellite manufacturer. you've got Maxar and Airbus up there with the most expensive, the highest quality. If I had to make a comparison between the different satellite manufacturers, these products here are kind of like your high-end Canon SLR camera, and you can get the lower end of the market that more like a Instamatic camera. They're cheaper. They're like a CubeSat, or probably about this kind of size, the size of a washing machine. Some of them are a bit smaller. Very cheap to launch, cheap to manufacture. Lifespan is only 2 or 3 years. Lifespan of these is around about 10 years. So totally different. But in terms of a quality of the image that you get, you know, these ones are the top shelf, basically. So this is like the Neo, that's sort of the equivalent. That's it, kind of nicely packaged up in its pod on the ready to go on the rocket, just prior to launch. The good thing about the Neo one is it gives you TriStereo capability. So I said I'd mention TriStereo, and I'll talk about that a bit later. It's got 6 multispectral bands, so ideal for vegetation, but also for could be for mineral exploration as well. There's just an image of an optical image of a mine, quite an impressive looking mine, but just in terms of looking what a 30 centimeter resolution looks like, we could really zoom down quite deep into that. So in terms of Swirl, actually, has anybody used satellites at all in the work here in the audience? Oh yeah, what sort of things have you been using it for? Yeah.
We're using it to render the stuff into Geoimage.
Oh, okay. Good on you. You get a prize for that.
Yeah. Using it and the seismic surveys to work out where we get the lines.
Yeah.
With trees and stuff like that.
Yeah. Okay. No, that's good. So a lot of the work that we do, particularly like in South America, where the terrain is conducive to it, is using the shortwave infrared. So I'm not sure how many of you are familiar with the actual spectrum, but we've obviously got the visible spectrum we represent as RGB in typical pictures that were taken by a camera or your phone or whatever you need. But, you know, this is typically what the human eye can see. And then we kind of move into the near infrared, and then just beyond the near infrared is the actual shortwave infrared. And shortwave infrared is actually a really nice kind of spot on the EM spectrum in terms of identifying certain types of materials, not only geological, but also man-made materials. And so it's of great interest to a lot of our clients. And then the other one of interest is also thermal infrared. So we do have some of our clients that are very interested in thermal infrared, and I think that's going to be an area of growth in the future. Just to show you what the difference is between, say, Swirl and the visible spectrum. So the apple looks nice and healthy in the visible spectrum. In Swirl, actually you can see this kind of decay. It's a rotten apple, basically. So it's quite a nice little example, I think, of looking beyond the visible spectrum. And here's probably a nice one for anyone who's interested in exploring for massive sulfides. We do get a lot of work in, say, Chile and Peru with people that are looking over greenfields areas, want to try and identify targets. They use Swirl. We actually work with a consultant who has an AI algorithm sort of trained specifically for geological targeting of clay microcarbonates. And so this is the type of presentation that you can actually extract directly from the Swirl data itself after some analysis. There's a couple of sensors that are around for Swirl. Asta has been around for quite a few years. You know, it's kind of like up there with Landsat. It's a bit iconic. It goes around the planet and just captures regularly. It's got a really nice swath width, covers a lot of ground. And so on the left-hand side here, you can actually see This is an Asta one. I mean, the reason I've put this in really is to show the difference in ground resolution. So compared to this one here, which is obviously a lot more, detailed, this one comes off of one of the Maxar satellites called Worldview III. So the difference here, that says 7.5, but it's actually 3.7 meters now. It was only 7.5 when they initially launched it. It's actually 3.7 meter resolution, ground resolution, so it's very good resolution. 16 bands, 8 bands in the visible spectrum, and then 8 bands in the Swirl spectrum. These numbers here, S3, S6, S7, refer to the actual band numbers. So the S is Swirl. So we're actually looking at Swirl 3, Swirl band 6, and Swirl band 7. If you combine them and then show them in any kind of visual display that has an RGB representation, you'll get this color representation. But these colors now are actually representing, the chemical reaction, basically the reflectance from particular materials. So at a molecular level, how the ground is reflecting the energy in that part of the electromagnetic spectrum. And so that's what's really of interest for us. The other good thing about the Worldview III satellite is that it does have a special device on it called the CAVIS, C-A-V-I-S. I'll show it in the next slide. It's really good at detecting clouds, aerosols, and water vapor. So you can imagine up in space, orbits, orbiting the Earth a certain number of distance, a certain sort of distance from the planet. They're actually measuring the response from the ground back up to the satellite. So anything that's in between the ground and the satellite has some impact. So aerosols from pollution, clouds, particularly in the optical range, clouds get, affect that response. And water vapor in general as well. So just haze, general haze, it all affects the response. And so this is in Beijing. This is the original image. If you just looked at it and processed it, that's what you'd see. But if you take out all the pollutants or the water vapor, this is what it really should look like. And this is the satellite itself. So, I mean, it doesn't look that impressive, but Worldview III, it's state of the art until the new constellation gets launched later this year. This is the primary telescope. It's got a focal length of 16 meters. Now, so this is actually orbiting around about between 550 and 600 kilometers above the Earth, and it can resolve something down to 30 centimeters. So I'm trying to think what the analogy would be. I think it was something, I think Townsville might be, maybe Rockhampton. It would be like someone standing in Rockhampton with a camera and taking a photograph towards Brisbane, and identifying something that gets photographed to that. That's the kind of technology that we're looking at, which I find absolutely fascinating. And here we just have a couple of responses from the different satellites over the years. The Worldview one was one of the earlier ones. It just took a panchromatic view, so basically black and white. Worldview II is just color, but it didn't have the swirl. And then we have the Worldview III with the actual swirl. Same area, but you can actually see we're starting to highlight, different responses from that ground material. And this one was just a point of interest, just to sort of highlight the level of detail that you can see from space. A lot of people think, oh, the satellite's just looking directly down, so you'd see everything in a top-down view, but that's not the case. The satellite's actually quite agile, and they can turn their sensors from side to side, so they'll actually track across the Earth in one direction, and the sensor will flip from side to side to that and take those images. And so you can get this. I mean, this is not good from an exploration point of view and mining point of view. You just typically want to look straight down, but some interest to some people. So why is Swirl special? So, most of the sensors, the visible range, we're in this part of the spectrum here. This is the reflectance value. So it's the amount of energy that gets reflected back up from the ground, from different materials. We have the near infrared, and then the short wave infrared here. And then beyond that, we have medium wave and the long wave. This area, we're sort of going into hyperspectral territory, and that's still I think it's got a lot of potential, but it's not been fully explored at this point in time. So material signature absorption features, I don't know about the actual physics of the material properties themselves, but this is the sweet spot, as we call it. So this area in here that we can actually sense with both Swirl and Asta data is really important for us because it gives us certain characteristics, reflecting characteristics that really allow us to look at different mineralogy. So again, we've got Asta versus the Worldview III. One, it's pretty much showing the difference in resolution. Asta is free. So that's the real benefit. And if you're looking at a large area, then Asta is a great thing to have because all you need to do is actually process the data and then, hey, presto, you can get some useful information out of it. Worldview 3, you actually need to pay for, but you get a much higher resolution. And then in terms of using it, these are the actual responses. So anyone that's actually interested in looking at these particular mineral assemblages, you know, we have a particular spectral signature that you can use. And that's what we look for in the actual response. So instead of looking at the optical image, we're actually looking at the spectral response. And then we can do things like machine learning to actually identify and map those areas within a particular area that we've captured with this kind of spectral information. And just to give you an idea, so we've got, this is the normal sort of camera picture that you would take. Good old Landsat 8, 30-meter resolution. You know, it can capture things in this area and also a bit of shortwave infrared. Asta came along a bit later. It's got a higher resolution, 15 meters optical, 30 meters in the Swirl range. You can see a few things as well. And then the Worldview 2 and 3, 1.2 meter optical resolution, and then the 3.7 meter Swirl. And so you can start to see some of these things. These are the wavelengths. You know, has differentiation of particular material properties. And this is what it kind of looks like after it's been processed. So you can actually see the different mineralogy here, calcite in blue here. And so in terms of like exploring, if you're into gold, you're into copper, any sort of massive sulfide deposits, you know, this would be very valuable information. If you've got like a blank sheet and you're really wanting to target some smaller areas to go and send your drill rigs out or do a bit more targeted exploration, you know, this is pretty good. And if we actually look at the actual spectral response or spectral signature for the different mineralogies, so allanite, and this is what it looks like in terms of the image itself. This is just showing the difference in resolution of Asta versus Worldview 3. So there's just a kind of a, this one probably not so much, but in the next one, you'll start to see Worldview 3, maybe not so much that one either, but this one here, an iron feature. So this resolution here that you're seeing on the jarosite, in fact, I just had a call this morning from someone who said, I need to find jarosite. You know, what can you do? I said, okay, Worldview 3, Swirl bands, we can do that. And so it is, some people are actually looking for it. And probably the work that we've got most recently in quarries is for lithium. It's become a really hot topic. So people are ringing us up now and saying, we want to see lithium. We need to look at the Swirl bands over a particular area. And there are definitely some papers out there. We're doing some studies at the moment to see the efficacy of that, but there are definitely some case studies where Swirl has been used for lithium exploration. Anybody here in that part of the world in terms of exploring for lithium? No? I think I came to the wrong venue. All right, we'll move on to DEMs. So everyone knows what a DEM is? Digital elevation model, yeah. So that's, again, we're talking about different resolutions from different sensors. So let's go back. Worldview 3, Worldview 2, and Geo1 gives this really nice high resolution DEMs. This one here, SRTM. Anyone heard of SRTM? Oh, okay, this is an opportunity for a prize. Can you tell me what the source is of SRTM? Yeah? Space shuttle, brilliant. That's fantastic. Yeah, I don't have any hats left. I'm afraid you have to take an umbrella. I'll put that over there. Yeah, so that's actually the space shuttle. So that flew missions around the Earth and collected data that's then transformed into a global DEM, about a 30-meter resolution, 30-meter vertical, 30-meter vertical accuracy. And then the ALOS Prism, ALOS is a sensor that's from Japan. They built that and they do a global DEM as well, which is a lot more accurate. It's like 2.5 meter to 5 meter vertical. Now, TriStereo has come out in the recent years. It's really good because if you're looking, the problem with stereo, so in other words, you're getting two sites of a particular target. If you've got a target like this, the satellite tracks over like this, what it will do, it'll get to this point, it will take an image, capture an image, or fly past what we call the nadir to the next point, and then take another image. So you've got this image with an offset angle, basically. And then from that, you can calculate the actual depth of your target. The problem with that is based, dependent on the orientation of what you're focusing on and the orbit track, you could get kind of shadows. You can get shadows like this, which is not so good. So this is the Kalgoorlie Super Pit. With TriStereo, you actually have 3 captures. You have one offset, you have one at nadir, and then you have another one offset as well. And so you get a much better detail resolved. And the really good thing about TriStereo is the cost to the end client is only a little bit more than the cost of stereo. And that's because the TriStereo is actually easier to process. But with the DEM one, there's some manual processes involved to try and resolve things like this as best you can. The TriStereo capture, you actually got more data, you got less noise, you got less variables that you're trying to deal with. So even though the cost of the data is greater by a third, your processing cost is actually less. So the difference between stereo and TriStereo is really quite small. So there's no reason why you wouldn't go for TriStereo every time. And the latest satellites, the Airbus Neo one is a TriStereo. So it's capturing, it's a 50 centimeter. You'll capture a 50 centimeter DEM with that, no problem at all. Very accurate. Just another example here, just showing the amount of detail that you can get from DEM, from space, and then just a nice little pretty shot. Satellite imagery draped over a DEM. Anyone know the difference between a DTM and a DSM? If you read this slide, you'll know the difference. Yeah, so some people get confused, but digital elevation model is kind of an umbrella term, I think, in the industry. But we like, a lot of our clients say we want a DTM or we want a DSM. The DSM is just the surface. So it's what gets reflected is that first reflection from the surface. So if you've got a forest, basically, you'll be getting the top of the trees, the canopy. The DTM is the digital terrain model. It's the bare earth model. So basically, you want buildings removed, you want trees removed, you want rocks removed. And so it takes a lot more work to produce a DTM compared to a DSM. And this is just sort of showing that example. So a DTM is a lot smoother, and the DSM obviously contains all of this information, so all sorts of buildings and structures. Operational stage, so we do work with operational mines a fair bit, and what they're interested in is radar. InSAR's become really popular since the tailings dams collapses in Brazil a few years ago. That's been a bit of a game changer, and change detection too is always, it's a really big topic at the moment as well. So in terms of radar, we call it SAR. Anyone heard of that term before? Synthetic aperture radar, yeah. It's just it's an artificial way of basically increasing the aperture size. And basically, it's the satellite is like in 2 different positions. So they use a tandem satellite to capture the radar response. So active, obviously, is transmitting a radio wave down to the planet, reflecting it back up. In fact, every single day, we have been being bombarded by radio waves from the satellites in space, because they're constantly going overhead and capturing that information. But I guess you can see, I mean, this is just off Dubai, the coast there, the artificial islands that they've created, the optical one, but then you can see all these little channels and things that come up in the radar. So really the radar allows us to give an insight. It really responds to different textures. Yeah, it's really quite amazing. And you'll see these darker areas here. Basically, there's no radio response, there's no reflection. So in general, water won't give you a reflection. So radar can be used for water mapping in general. There's a few exceptions, as there are to every rule in geophysics, I think. But as a general, it's a rule of thumb. You know, radar is quite good for flood mapping. But in terms of looking at those structures too, it really does give you a different insight. This is the actual bird that captures radar. So this is called TriStereo, operated by Airbus. So this is the actual sensor here on that bottom thing. That's the radar antenna. This antenna is a communication antenna. So if you like, basically what happens is this collects all the data, gets stored on board, a little bit of processing, and then it gets transmitted down to what they call as a ground segment on planet Earth. And then on the ground segment, it's been transmitted to a processing center somewhere. This one goes actually every 11 days, not 12 days, but it actually revisit rate is 11 days. Millimeter accuracy. This can be processed. The data from TerraStar can be processed, and we've been doing quite a bit of work in this space to millimeter accuracy. So we're measuring changes in surface movement down to millimeters. We typically look at the velocity, and we refer to it as millimeters per year. In terms of the theory, because people will say, hey, Mark, how is it that something that's orbiting like 600 kilometers above the Earth can resolve something down to less than 1 millimeter on the ground? That doesn't seem right. And it doesn't, unless you understand that radio waves, doesn't matter how far they propagate, they're not going to change in terms of their phase component. And so what we're looking at is actually the phase component at the radio wave as it touches the surface and then reflects back up, and we're actually measuring the change in that phase component. So if we look at this diagram, and you imagine at the start point, his point, it's at that point there as part of the wave cycle, gets reflected back up, it's measured, it comes back over 11 days later, the ground's changed, and the phase coming back up from that reflection point is actually gone through a phase shift. We're actually measuring the phase shift. So we have to do this phase unwrapping. There's a lot of complicated processing that goes involved into actually generating a result from this. The end result is actually really impressive. And so I know you're an explorationist and this is mining, but just bear with me. So this is Incadia. This is a massive collapse of a tailings dam wall back in 2018. And this is the INSAR. So here's the tailings dam wall here. It's one tailings dam, and this is actually a southern tailings dam too. So fortunately for this mine, or maybe not fortunately, but you know, this is where there was a point of failure. So it really does stand up. But this was like 1 month. This was a month before the actual failure occurred. You know, at the end of the day, it's no good saying, oh, he had a collapse, unless you can predict it and then do something to prevent it. You know, where's the real value? So if we actually look at the time series for that particular point here, you'll see it's fairly steady, and that's probably what you'd expect with normal settlement of a tailings dam wall over time. You know, as it starts to compact, it will start to sort of subside to some degree. But at this point here, and around January of this year, there's actually a definite change in the gradient, or an acceleration, if you like. Maybe if you got to this point, you'd say, oh, maybe it's just an outlier. You get to the second point, is there something going on here? You get to the third point and you think, yeah, that's something, we need to investigate this more. You probably wouldn't, if you're the geotechnical engineer, you wouldn't be saying, I won't worry about that. Not when you've got millions and tons of toxic material there that's ready to spill out. So, yeah, so it's quite an amazing technology that we're using now. So just a couple of examples of Hunter Valley coal mining district. The red spots represent where you've got downward acceleration. So in the millimeters, you might not be able to see that, it's millimeters per year. It goes from -30 to +30. That kind of yellow color is pretty neutral, so you know everything's stable. And then blue, if there's any blue, that would be actually a bit of uplift. And that's kind of zooming in again, so you can just see the resolution there. And then again, so each one of these points is collected every 1 meter. So spatial resolution, and there's various ones that you can use. There's 1 meter, there's 3 meters, 5 meters. So as a client, you can say, I want actually really high spatial resolution. I want 1 meter. You probably wouldn't use that in exploration, but we have clients in the residential development business, and we're monitoring houses, and they want to know what's happening at the back of the house compared to the front of the house and the next door neighbors, and what's happening on the streets. And they want the 1 meter spatial resolution. And then when you can pick the time series, 2 different points, it's really obvious that this point here in red is actually, the velocity of that is it's going down at a rate of knots, you know, compared to this one, which is really constant. So it is really quite a useful tool. Change detection. So this is the dashboard that we've created at Geoimage. It's basically just pulling together different bits of information. A lot of our clients are into monitoring, especially with rehabilitation and construction around mine sites. You know, you need to be careful that you're not going beyond your envelope of work. And so, you know, we developed this dashboard, capturing data, capturing imagery, say every 2 weeks, processing that, put it into the dashboard, streaming it as a WMS service, and coming up with results like this, and automatically using machine learning to generate the change vectors. So what's actually changed between epochs, you know, and the great thing about this is that you've got a record. It's an auditable record. You've got the imagery. So if something happens down the track, you can say, well, on the 5th of May, this is what the ground looked like. And you know, on the 25th of May, this is how it changed. And you've got a really good track record of what's going on. And it calculates the area that's changed per epoch. You can filter it, you can zoom in, all the usual things that you'd expect from, it's got a little video. I won't go through, it's got no time to push it on a bit. But yeah, it's just going quickly going through. This area, like this train, we were monitoring this for 2 years, and it just the amount of construction week by week was absolutely incredible. I might just, there we go. Yeah, so that actually that red band there, that is actually the work permit for this mine site. They're not allowed to clear outside of that. And you can see what's going on over time. That's actually the change detection in action. So you see the polygons that are generated through our algorithm, the number of hectares, the acquisition date, and we give each change a unique ID. Yeah, so it's a pretty handy tool, simple to use. NDVI, I won't go into that. It's just another way we can just use spectral signatures. We can do band arithmetic, which means we take the different bands that we capture. RGB, near infrared, is common. And then you can actually do some, it's like adding and subtracting and division of those bands. And from that, you can actually highlight different properties of the ground itself. The vegetation, this one, is called the Normalized Difference Vegetation Index, NDVI. So the red areas here actually represent vegetation that's more healthy, you know, than the other vegetation. The blue is the ground, so it's no vegetation there whatsoever. The yellow is not so healthy, but really the red stuff is the really healthy stuff. And so a lot of our clients in the agricultural industry are looking at this sort of thing. It's not a magic bullet though. You know, people they jump on these things, they say NDVI, I'll do this, you know, it's going to get me. You got to know what crop it is. You need to understand. You need to do the ground truthing. You know, the same thing with all geophysics, right? You can take it, but don't just apply it holus bolus against every single scenario and expect you're going to get the right answer. Multispectral analysis. So we do a bit of this. So in terms of again looking at different species have a different response. Sometimes at the moment we're looking at table grapes and differentiating different types of table grapes in Mildura. I'm hoping to go down and do some ground truthing myself, but we'll see how that works out. And then our partners. So I think, you know, Geoimage, you know, what we want to be is we need to have a diversity in terms of what we can provide our clients. And so we are looking at, we have the very high resolution data, 30 centimeters. We've got worldwide DEMs at 2.5 meters. Pixel, that's a startup from India. It's going to change hyperspectral. Hyperspectral we didn't really talk about much, but it's going well beyond the Swirl band. Lots and lots, it's hundreds, literally hundreds of bands. There's been a little research done on that because it's not that available, and what is available is actually quite expensive. So I think these guys are going to be a game changer for us, and we're going to start looking at what this can do in the exploration industry for sure. And the resolution is 25 meters, which is a lot compared to say 0.3, but compared to what else is out there, it's really good resolution, really good. Black sky, it's a targeted, it's like intradaily, small spot targets. There was a client, they had a mine site offshore. They had to move it for political reasons. It was unrest on that island, but they were keeping an eye on it every day from space. And they noticed somebody was going in and stealing trucks from the compound. And so they rang up the local authorities and said, hey, someone's just taken our truck. You know, can you go and look for it? So, you know, there's lots of different use cases. Synspective, this is also another game changer. So a radar every day, every single day. And when we think about natural disasters, radar can penetrate cloud. That's its big advantage over optical. It will go right through cloud, it will go through smoke. So bushfire detection and monitoring, flood detection and monitoring, you know, this is also going to be a game changer for us, I think. And then GHGSat, another startup from North America that we're partnering with. So they've got a sensor now that directly detects methane. They don't care about anything else. They're just focused on detecting methane. And next year, they're going to launch one for CO2 monitoring. So, and the resolution for the methane sensor is, again, about 25 meters. So that's enough to identify, say, a leak from a pipeline or a well pad and differentiate it from other well pads instead of just, at the moment, you can detect methane, but it's in the upper atmosphere. So you don't know exactly where it's coming from. All right, glimpse of the future. So this is Mark's top picks for what's going to happen in the next few years. Intradaily revisit of optical and multispectral, that's going to be here by the end of this year. That's so close that if you want 30 centimeter over your mine site or exploration site, you can have that any place in the world. Around the equator, you'll get it more frequently, maybe 3 or 4 times a day. Around Australian latitudes, yeah, probably at least twice a day. STAR, similar, another game changer by next year, sometime next year. So that startup's Inspective. It's actually a Japanese startup. So they're launching more and more satellites every few months. Increase in the hyperspectral resolution. Daily revisit. We didn't really talk about thermal infrared. That's something too, like in exploration. That is something, if you've got a mineral assemblage that has a particular thermal signature, and some of them do, then you can actually use thermal infrared, you know, to explore for that particular mineral assembly. So, you know, again, there's use cases there. That's also been underutilized. And I think the real driver for that is heat island, urban heat island mapping. That has become really a big theme because of global warming. And so there's a lot of research now going on into how we're going to measure, how we're going to monitor the urban heat island effect. So I think that's really pushing this. But I think that the side of thing will be exploration as well. And then increasing native resolution to 15 centimeters. I think that's going to go. I've got 2024 and with a question mark. The technology already exists. It's not because you can't do it. It's because there's an international treaty that stops commercial use of that. Military can get it, 15 centimeter, but no one else can. But I think that will get relaxed. I think that will get relaxed in the next few years. Yeah, so that's it. Thanks for listening. Any questions? Oh yeah.
The Maxar technology, that's American company, isn't it?
Yeah, North American, yeah.
I see they're providing a lot of a lot in Ukraine, what's happening in Ukraine.
Yeah, that's right.
A lot of detail
Yeah.
there, what's happening and
Yeah.
the resolution.
Yeah.
So, wonder who's paying for that? Who's paying?
Australia, American Defence.
Okay.
Yeah. Yeah, Maxar actually have a lot of their revenue comes from the US Defence. So what's right? I guess I didn't sort of go. I mean, there's so many things you could talk about, but one of the things when you're what we call tasking a satellite is that we can actually control or program the satellites from our office in Geoimage, and so we want to capture this particular area of interest, you know, whether it's in the Pilbara, whether it's in Ukraine, anywhere around the world, and we work all around the world. One of the factors is the weather. If it's going to be, and so they will do a feasibility study, and so what's the weather forecast? It's going to be cloudy. If it's going to be cloudy, there's no point. But the other one is the competition. You know, there's limited storage on board the satellite itself. It's got a finite hard drive, right? And so if you're flying over somewhere and it's a geopolitical hotspot, then you have a lot of clients saying, I want imagery over, say, Ukraine, for example. And so US defense gets highest priority with Maxar because they've got contracts with them and they're obviously paying good money. So if you're a commercial company, an exploration company, and you're interested in capturing something over Ukraine from a geological perspective, you know, it's probably you're going to be a bit down the queue, so to speak, you know. Whereas Airbus, they don't have that same relationship. So for us, Airbus, if we've got a regular capture we want to do across Australia, you know, Airbus is quite good in terms of there's capacity on board the satellites. Depends on which satellite it is too. There's a few variables. But by and large, yeah, Airbus has been pretty good. Good question. Yeah.
Mark, I'm wondering, the monitoring of tailings dams or dams,
Yeah.
do you see that is that seen as a nice to have by industry, or is that increasingly data that's actually by other regulators?
Yeah, it's not. That's a good question too. It's no longer a nice to have. You know, since those disasters in Brazil, when there was maybe 300 or 400 people lost their lives and it was damage to property, there was you know, a huge amount of environmental damage as well. The Church of England Pension Fund went out because the Church of England Pension Fund actually has trillions of dollars invested in mining globally. And so they said, we want transparency. We want to know about these tailings dams and how they're being managed. And so they kind of put the mining industry on notice about 3 years ago and said, you need to actually disclose how old your mines are, what the capacity, what is the actual design for those mines, you know, what risk management strategies you have in place. And so a lot of the big companies did the right thing and they've published that. You can access that, it's in the public domain. But some of the big companies too, the mining companies said, hey, we have to lift our game. And so they created like an international committee basically for management of tailings dams. And so now it really is forcing the industry to take on board those other tools as well. But InSAR is definitely one of the tools that the big players are saying, yeah, we actually need to do this, you know, because the great thing about satellite is like you don't need to be on site. There is no safety issues. It's totally remote. You know, in areas where it's inaccessible for whatever reason, you know, the satellites, there's no way we can hide from a satellite these days, right? So, you know, it's ubiquitous. It's got a regular cadence, like it's 11 days for the TriStereo satellites, and the other ones are similar as well, the other satellites. So it's a really good solution in terms of, and you can measure down to that millimeter accuracy too. So, you know, it ticks quite a few boxes.
Have you got anything that works in that shallow water space? You know, like what's the best?
Yeah, there is like some of there are some, it depends on what is shallow, how do you define shallow, 2 or 3 meters. Some of them will penetrate to 2 or 3 meters if it's clear water. So we do have that. I'm probably not the expert on that area, but we definitely do have some of our clients because they're interested in the shallow water around on the coastal, it's a bit like mangrove swap mapping, those sorts of things, and a few other sort of tidal species that they're mapping. So mostly from the environmental sector, and people that want to map in different species and look to see what that tidal kind of plane is looking like. But there is a limit, you know, probably even in clear water, I don't think you'd probably go below like 4 meters.
I don't have any questions online at the moment.
I got some more.
Oh, yeah.
Just about resolution and precision. So like, if you ignore hardware limits, then I don't know, is accuracy? I'm just wondering, like, what's your ultimate goal, or what could be possible in terms of horizontal resolution, also vertical precision? Are you getting close to LiDAR, or will you get that?
Yeah, that is a really good question. In terms of in terms of the physics and the hardware, I think it will probably come down to economics to some degree. Well, will it rival LiDAR? Yes, that's a tough. Yeah, that's right. Yeah. I mean, there's definitely. I think what's happening. I said this right at the start. Is there's been an explosion in the last 2 years, because now you've got like ride sharing facilities. Now you don't have to buy. Well, you don't have to pay for, you know, a few $1 million to launch your satellite, because you can build a small satellite, put it on a rocket with 5 or 6 other companies that have got 10 satellites that they're launching, and it goes up into space. So you're seeing all of a sudden this great explosion in technology advances. And sure, they might not have the same optical resolution as the big players like Airbus and Maxar, because they've spent $3 or $4 billion on their latest satellites, and they're about the same. Well, they used to be about the same size of the sedan car. Now they're smaller than that, but still fairly hefty. So I wouldn't rule it out, because Moore's law. That's right. It's going to come. I think it's going to come. You know, the interest in space is phenomenal. I mean, we've got our own space agency here now in Australia. There's a lot of money that's going into that technology. So I really see it as a big future. I mean, probably the biggest problem with space is the congestion up there. There's so many satellites going up now.
So when you talked about 1 and 2 millimeter precision, that's differential, right?
Yeah, the millimeter, yeah.
Like actual elevation compared to surveying it in, how accurate is that?
Yeah, that depends on your ground control that you use as your reference points. Yeah, so that will probably be, that could be like 50 centimeters if you're using a really good DEM. But in terms of the clients, what they're looking for is that relative change. You know, that's really important to them. So the actual absolute value is not so important. I mean, if they want a DEM, you can get a DEM. But what the value of surface movement monitoring is looking at the rate of change. And whether that rate of change changes, the acceleration. And that's the real key, because structures, you know, they have a certain amount of give to them. And if you go beyond those thresholds, they start to fall apart. Yeah. But it's amazing. We're doing a project at the moment. I can't kind of talk about it without, you know, the usual thing happening to me. But the accuracy we've shown, the accuracy is less than 1 millimeter, sub 1 millimeter. Yeah, that's pretty good. Yeah, I'm impressed. Yeah.
With the so the satellite goes out every 11 days now.
Yeah.
But if you want to see what's happening on a daily basis,
yeah,
sending satellites up there, you make them can't do, like,
yeah, well, that's what I was saying with the other company, Synspective, that's a startup. You know, they've got some venture capital, and they're building a whole constellation of radar satellites. And so that it's going to be daily. That will be daily, and that will be next year. They've already launched some. There's launching more this year. And so that, you know, that does change things from things like maritime monitoring, if you're monitoring ships out at sea, because not all the ships are using the beacons. They all should use a beacon, like an international radio system that goes via satellites. Sorry? Yeah, no, that's right. Yeah. Some of them, they're like, yeah, I won't mention any names, but some of them are not using that system, you know. And so the SAR is a really good way of detecting ships at sea. They just stand out like a proverbial. So, you know, lots of different use cases. Yeah. I mean, we've had police ring us up before and said, can you spot this black Mercedes on this highway at this certain time a year ago? Because we think there's a body in the boot. You know, it's like, yeah, that was hard because the satellites go over around 10:30 in the morning. But that won't be hard. Like in a couple of years' time, that we will say, yeah, sure. What time of day was it? Oh, yeah, we've got satellites that went over within 10 minutes of that. You know, that will become a ubiquitous thing. It won't be an issue. Like it'll be really, I don't want to say big brother, but oh, well, there you go, I said it. Yeah, it'll be constant monitoring. Yeah. No, nighttime as well. In fact, like the Asta one, that also captures at nighttime as well, and then we use that. We used that just recently to look at some urban heat effects actually on some residential estates. So the client wanted to compare their residential estate with someone else's residential estate because they've put in place a policy to try and cool their estate, and they wanted to see if it was actually working. So we wanted to measure the temperature at night time as well as during the day. Yeah, it's interesting.
Any more questions? Very much like, just before we go, I'll see you.
Is that? It's not a Geoimage umbrella, is it? Oh yeah. Thanks so much. Yeah, thanks. Thank you. Yeah. I don't know what's happening. Yeah, it's weird.
Do you mind if I shut down everything?
Yeah, that's okay. That's fine.
Yes, I understand.
Yes, there we are. I think it's ever as simple as it should be.
No, never. I don't mind a minute.
I'm going to close the computer down. That would definitely do it.
That'll definitely do it.
Yeah.
Oh, there you go. Kit. All right.
It doesn't, yeah, I don't know what's some of the responsible sheet is. It's pretty good. Anyway.
Thank you very much for that.
Yeah, no worries.
Not the usual ASEG meeting, but I was paying attention on the phone.
No, it's all good.
Yeah.